Good afternoon, everybody. I wanted to give a few helpful hints about theorem proving, and the first thing I'll do is I'll look at this critique of a proof that I put on quiz 1. And I think most of you figured out that the proof was not completely correct. But what was the problem? All right, well, let's first mention that this is a little harder theorem to decipher because it's not an if-then format. It just says in the 4-point geometry, each line has at least one line that's parallel to it. So let's make that an if-then statement, some givens and a conclusion, right? If a line exists in the 4-point geometry, then at least one line is parallel to it. Okay, so if we have a line in the 4-point geometry, then there is a line parallel to it. And how do we prove that? These are all correct statements, especially 1, 2, and 3. 4, we can argue about that maybe 4 is not completely correct, but certainly 1, 2, and 3 are correct in terms of being correct statements. What's wrong with them? Well, let's talk about the proof outline. So if I have a line in the 4-point geometry, then, okay, so if I have a line in the 4-point geometry, okay, which line? Any line. If I have any line in the 4-point geometry, okay, so what do? Well, the proof, the direct proof from Math 2800, the intro to proofs is, I say, well, let there be a line in the 4-point geometry. Let there be an arbitrary line in the 4-point geometry. Why? Well, I want to start with any of the lines. You can pick any one you want in the 4-point geometry, any of the 6. Just pick one. Okay, and then I start with whichever one I'd like to, but I have to prove that there's a line that's parallel to it. Well, 4-point geometry is a square. So I end up with something like this. And if the points are A and B and C going around like this, and then D, well, then picking a line in the 4-point geometry is as simple as picking any of these 2 letters, right? 4, choose 2. There are 4 points, choose 2 of them. Okay. Then how do I find a line that's parallel to it? Well, it's the 4-point geometry, and 2 of them have to be on this arbitrary line. Okay. So pick the other 2 points. And the line that is on those 2 points, see by axiom 3, any 2 distinct points have exactly one line on both of them. So say you pick DB. So you pick this line here that goes from D to B. Okay, then I'm saying I'll pick A and C, and the line that connects them, let's just say, for example, it's this line. Then the line AC is parallel to DB. Okay, so that's the basic idea of this proof is pick any line you want to start the proof. Here you go. Pick any line you want, okay? And give me the name of that line, and without loss of generality, let's call it AB. Okay, line AB. Well, then pick the other 2 points that aren't A and B. Okay, CD are the 2 points I picked that aren't A and D. Then the line, right? So now we're talking about A and B, the line AB, and then I pick the line DC. And in fact, if I draw a line connecting the other 2 points in the geometry, then it's parallel to the original line. Okay, so just a little helpful hint there about what was actually wrong. And I also want to encourage you, I'm trying to give some proof tips in this as well as some other information. But how do I make a proof? Well, I have to start with the givens. And if it says all right triangles, if the proof starts off that all right triangles obey the Pythagorean theorem, how do I prove that? Well, If I have to prove it's true for everything in a set, I pick one arbitrary member of the set. So I say, let there be a right triangle. Okay, and it can be any right triangle. It's like your worst enemy gets to pick whatever the worst example is, the most malignant example of from the set. They're allowed to pick that one. Okay, so pick any right triangle, and then based on the right triangle that you picked, I'll prove that it obeys the Pythagorean theorem. Okay, so remember your Math 2800 Intro to proof techniques, how you prove things are true, how you start with the givens and you work your way through the proof to the conclusion. Okay, so let's think about theorems. Again, I want to help you think about these things more accurately so that the geometry proofs will be easier for you to see and understand and complete. Okay, so I often ask math majors the question, what is the Pythagorean theorem? And you know exactly what they say. They say a squared plus b squared equals c squared. And that's incorrect. That's just the conclusion. Then a squared plus b squared equals c squared. So let's make that theorem a little bit better, okay? Let's do an if and a then. All right, so if a right triangle has legs A and B and hypotenuse C, then the conclusion is a squared plus b squared equals c squared. All right, I kind of circled funky there so it was hard to see, right? So if a right triangle has legs A and B and hypotenuse C, right? So we call the legs the shortest two sides. The shortest two sides, oops. So this is not going to look like a great triangle, but there we go. So, right. The way this normally goes is C is the hypotenuse, and then A and B are the legs. By the way, the point A, which is capital, so points are capital, and the point A is across from the line A, right? And the point B is across from line B, and so lines are in lowercase letters and points are in uppercase letters. All right, well, that's not the world's biggest deal, but there you go. So why did I do that? I'm just trying to get you to think about the theorem. What is the theorem in its most primitive sense? It's an if-then statement. If given 1 and given 2 and given 3 are true, if the givens are true, then we have some conclusion. Okay. What's nice is that the givens are my starting place, right? I have to choose an object that has the given properties. So I would like to give you some proof tips, and I'll go over these in just a second. Let me mention one of the biggest proof tips I can give is to complete your proof project efforts 1 to 2 days early. That will give other people on your team a chance to look at the proofs that you've completed and see if they have any constructive criticism. They might see something, a line you forgot, or they may have a critique, and it might take less than 10 seconds to fix your proof. You just forgot something. Or there may be a major problem and they point it out and you're like, oh, and then you can go back and fix it. But I'll give you the points based on the time I grade it. So if you turn in your proof 2 days early and the next day somebody finds an error and then you fix that error, then I'll give you the points with all the errors fixed. So the point of the team proof project, at least for me, is so that you learn how to prove theorems, but also we learn a lot about proving theorems by reading other people's theorems and trying to figure out if they are actually a theorem, which is why I gave you an example. The example I gave you on quiz 1 was a proof that somebody tried in my class once upon a time. I won't name the student. It was actually a good student. And you know how it is, these early proofs, you're just getting used to geometry style proofs, and finite geometry is a little funky because we don't really have lines. We have line segments, but we're calling them lines. And we have places where lines obviously cross. Like in the 5-point geometry, we have places where they obviously cross, but we don't consider the points of intersection if I don't have a point there. So there are a few things that are weird in finite geometry and beginning geometry that you guys are getting used to. So I gave some help. I don't know if you read the grading document yet, but in the discussion list, I just put in there some, well, I graded everything, and you can see the hints I gave and what I said there. But one of the things I said was that I graded easy. I think that's appropriate. It was your first proof project. The proof is going, the grading is going to get a little more exacting as we go. So, but again, I thought it was good early on for me to help out a little bit, which is why I jumped into the conversation. The proofs were posted kind of late, so I just went ahead and made some comments to try to help people out, help the team start off with a good score. I will not be helping as much in the future, and I will be a little more exacting with the grading in the future, just letting you know that. Now, so in geometry, direct proofs are almost always possible, and they're very often the way we go. So we're talking about direct proofs. That's just follow your nose. Start with the givens and start making claim, claim, claim with their justifications, and then you reach the conclusion, a direct proof. Let me mention also that there is nothing wrong with having multiple drafts. First draft, second draft, third draft. And while they may be primitive and they may be in outline form, you'll find that most math professors write proofs in steps. Even proofs that we know we can do, we often have a first draft that is, we really wouldn't want to show anyone. It's pretty clunky. But once we see how the proof goes, then we can go back and we can make it cleaner and more illustrative, right? There are some proofs that are very illustrative. They help you understand the math meaning behind what's going on in the proof. But yes, math professors write multiple drafts of proofs, and don't be afraid, because sometimes the hardest thing to do is to get started. But the easiest way to get started is to understand that this is just a first draft. I'm just going to go as far as I can. I'm going to write down what I know. I'm going to justify what I know, and I'm going to see where I get. And often that process of writing the first draft of the proof actually is the thing that helps you see, oh, I see what's going on mathematically here. Now I know what I need to prove. And again, start with the givens, make your one-step inferences, and reset. You know, that is really good advice on any proof. If you don't know where to go, just take the givens, make inferences that you can justify, and don't try to go to big ones. Just try to go that, oh, I used 2 points of the 4-point geometry. That means there's 2 more. 2 other points. Oh, okay. And then I also want to emphasize, one reason I have you working with GeoGebra is that it really does help to have a dynamic drawing. And you can test your ideas mathematically. The first step in theorem proving is not writing down the proof. The first step in theorem proving is figuring out what's going on mathematically. Sometimes just drawing up the figure in the givens is what you need to do. And then by playing around in GeoGebra and animating certain points or just dragging the figure around, you start to see what relationships are true, and you can figure out which areas are equal to what and which angles are equal to each other and that sort of thing. So it's just a really good idea in GeoGebra to make a dynamic drawing and test your ideas. And then probably one of the most difficult things in geometry is the proof by picture trap. Oops, I'm sorry, I was trying to underline that for you. There we go, proof by picture trap. And what does that mean? That means that sometimes you can accidentally draw the one figure, like the one right triangle that it happens to be true for. So you're trying to prove a theorem, and you accidentally draw the picture that makes it sort of obviously true. But that's not all right triangles, right? There may be other right triangles for which that doesn't work. So you've got to be careful about the picture. And then this is also a good reason to talk about starting with finite geometry, because certain things in finite geometry, you feel yourself going, well, look at the picture, dang it. If you want to see why this is true, if you want to see that every line has a parallel line to it, just look at the figure. And any line you pick, you can find one that's parallel to it. Well, okay, but that's not a proof. So be careful of the proof by picture trap. Also, in finite geometry, the pictures that I've given in the notes are not necessarily the only model. They are models, they are working models, they're good models, but they're not necessarily the only way you could draw it. So just be careful of the proof by picture. Um, Also know proofs by contradiction are cool. I like them. A lot of times if you're having trouble proving it directly, negate the statement and try to disprove it. Um, that can help you learn what's going on mathematically. I think that of more as a problem-solving step. But in this course, you're going to see very few proofs proceed by contradiction, and almost none of them proceed by induction. Okay, so when you're thinking about how to prove something, definitely go to the direct proof. Try that first. And you probably won't need any more elaborate things than that. You may. I mean, there are certain situations. But for instance, a proof by contrapositive. There may be a couple of places in geometry where that's helpful, but they're pretty isolated. Generally speaking, you're not going to do something elaborate with your proof technique. You're just going to use the basic, start with the givens, justify, end up with the conclusion. Now, when you're turning in a proof, I would like you to create and label a correctly drawn figure. Why? Well, it's a whole lot easier to read your proof if I know what line AC is and what line BD is. But if I don't have a figure, if you haven't included that in your proof, I'm sort of making it up as I go, kind of figuring out what you think is line AB or line AC. So definitely on quizzes where you have to provide a theorem or something, I'm going to leave a way for you to share your figures. Okay. Remember, for each claim, include a justification. Now, most of you did this well on Proof Project 1, the team project 1. But there were a couple statements that people made, and they were true statements, not arguing that they were true. They were true statements, but they didn't include a justification. Okay, so make sure that you're not only making true statements, true claims in your proof, make sure that you have a justification explaining why it's true. And I've already mentioned this. Remember your Intro to Proofs class. How do I prove that two sets are equal? Well, we usually do that by proving that if I'm trying to prove that sets A and B are equal, I prove that A is a subset of B and that B is a subset of A. And if that's true, if A is a subset of B and B is a subset of A, then A and B are equal. Why do I mention that? Well, when we're talking about the number of lines or the number of lines in a geometry like Fano's geometry, for example, we prove there are at least some number, and then we prove there are no more than that number, that if I have any more lines than that, it leads to a contradiction. Oh, and there we go. I just said contradiction. So occasionally, we do use something other than direct proofs. And then I do want to talk about dynamic GeoGebra proofs. Oops, let me get rid of that and talk about the dynamic GeoGebra proofs. So think about this. Let's say the next set of proofs are due on Wednesday, which is about what's going to be true, a week from today. I'm going to hopefully get that assignment done right after I do this video. And say they're due on Wednesday, and you just put your proof in a dynamic GeoGebra drawing, and you post it on Monday. And then somebody finds a little error. It's not that big a deal. You have to change a few words on a couple different lines. Here's the nice thing. If you have your whole proof as a dynamic GeoGebra proof, you can just edit it. And the great thing is, I will grade the final version, okay? You can even edit after the deadline, as long as you as long as you edit it before I grade it. But right, you can turn something in and it's turned in form. Usually when you turn something in, right, you've written it on paper and you're handing it to the professor. But we've got this nice situation where you can hand in your proof, it's just a link to your GeoGebra file, and you can update it, okay? So it makes them really easy to share in the discussion list. And if you see a problem, then it usually takes less time. You don't have to redo the whole thing. You just go back to the original drawing with the same link. And then all you have to do is just post in the discussion, hey, thanks for the suggestion. I made updates. You can check the figure. And so it's really easy to get feedback on dynamic GeoGebra proofs. So I'm just going to make a big plug for these dynamic GeoGebra proofs. Most everybody did their proofs directly in D2L, and they had a dynamic GeoGebra proof sort of lurking behind there. But we'll see. Maybe the next go round we'll have more dynamic GeoGebra proofs and fewer that are worked out in D2L. Okay, and then QED. And then if you're using $ mathematics, you can use this. A lot of people just put a little square. Sorry, that wasn't drawn real well. That looks like a square, a rectangle with a bite out of it. But some people do like to use the little square to end a proof. And in $ mathematics or what we call LaTeX, that is \square. Okay, and also at the beginning of the proof, write the word proof. Why? Well, you know that some people put some of the axioms in their proofs. And while that's not bad necessarily, if you just start a new line and write the word proof, and then start a new line and start your proof, let ABC be a right triangle, an arbitrary right triangle. If you start that way, then everybody knows where your proof starts. Also, a lot of people, and I don't know that I'm going to be able to spell the word proof, drawing with the cursor, because I don't have a mouse. I'm doing it with the mouse pad today. But that's kind of right. And then, so a lot of people will do, in parentheses afterwards, they'll say what kind of proof it is. Sorry. And I'm going to do by hashtag. This is a symbol that some mathematicians at the university where I got my PhD, they use the little hashtag symbol to mean by contradiction. And so if they put proof, parentheses, by hashtag, you just knew right away that they were going to go by contradiction. And so you were looking for that setup of the proof and you were looking for something negated, and then you were looking for the counterexample. You just knew what was coming. Same thing they would put by induction if they were going to do an induction proof, and you knew what to look for, or by contrapositive. So anyway, start the proof, and then, pro tips, you can actually use parentheses after the proof to alert the person who's reading your proof, i.e. the person who's grading your proof, exactly what you're doing. And it clears up a lot of things. And I know a lot of students feel like, oh, I don't want to clear it up. If I tell the professor exactly what I'm thinking, he'll realize I'm confused. Okay, well, I'm going to realize that. I'll just tell you this. Your math professors are going to realize that you're confused. If you're confused and that's causing a problem with how you're doing your proof, hiding details from your professor is not going to hide the fact that you're confused. What it does with and I'll just mention this, a correctly drawn and labeled figure and all the details that you can muster, that your reasoning may be correct. You may have the right proof outline, and you got A, B, and C, and E, but you didn't know point D. You didn't quite know how to get that part pushed through. Okay. Well, then it's a lot easier for somebody reading your proof, one of your teammates or the person who's grading it, to go, oh, I see what kind of proof it is. Oh, there's just this little misunderstanding here in point D. They got the other 4 points right. It's a correct proof outline, and if we can just patch up this little bit here at point D, then we have a proper proof. Okay, so again, putting proof at the beginning and a QED or a little square at the end, just again, it helps the person who's reading your proof see exactly what you're doing. And give them as many details as you can, not fewer. I know you guys are trying to write nice proofs, which also includes being brief when possible, but don't be so brief that you leave out details that are needed. Okay, so I also want to mention something about the textbook. So um, let's say you're proving theorem 1.1.4. Okay, so you're doing the fourth theorem. You can use theorems 1, 2, and 3 even before they're proven. So you get to assume that everything prior to your theorem is proven. So I think in theorem 4, you could actually use theorem 2 to help save a step or two. You don't have to reprove theorem 2 as part of theorem 4. If you need it to be true, just quote theorem 2 as because theorem 2. And I wanted to alert you to that because we're going to be doing more of these, and we're going to start into Euclidean geometry where there's a bunch of axioms and a bunch of theorems. But here's the thing. If you're proving theorem 20, you get to assume that theorems 1 through 19 are true and have been proven. Okay, and maybe somebody else's assignment to actually prove them, but you don't have to go back, oh, I want to use theorem 12, so I have to prove theorem 12 before I can do my theorem 20 proof. No, just quote theorem 12. We don't have to quote it, but refer to theorem 12 to get the conclusion you need, the justification you need, and then you'll be able to do your proof of theorem 20. All right, so remember that you're allowed to use prior theorems. Now, in the finite geometry section, it's going to work that you can only use the prior theorems on that page because, again, the theorems are different, say, for the 5-point geometry than they are for Fano's geometry or Young's geometry. Now, in the next section, when we start into neutral geometry, which narrows down later to just Euclidean geometry. So when we're in the next two sections, the theorems go on and on and on. And, you might have theorems that you go back 5 or 6 pages to grab the theorem that you need. If you're proving theorem 62, you might go all the way back to theorem 41. That's the theorem you need to help you, justify your theorem, justify your proof. Well, that's about all of the proof tips, pro tips I can give. I was exceptionally impressed with your first team project. I graded it gently and I gave comments on the proofs to try to assist. So good. You guys hopefully achieved your goals. You got a good grade and you got a better understanding of what it is that I want. And I was able to be nice and to grade gently and to give you that good grade and encourage you to just learn more and do a little bit better each time as we go forward. And I hope you have a wonderful day.